Thank you very much for the invitation. I was not aware of this nice group in Italy, so that's good. So I will talk. I was asked, and then I was considering what to talk about, and then you could either go deep into one subject or describe a few subjects more briefly, and I decided to go for the later. So I will actually talk about three different projects that I have been involved with. So the first one is with Lasse Leskilä, a professor from Finland, Aalto University. The second one is more applied, that is with a PhD student and a former postdoc of mine. And the third one is the most recent, and that's with Frank Ball and Pete Neal, who are from University of Nottingham in UK. As Francesca said, I have been involved in a summer program. So before I start, a small advertisement about this. ESPIDAM, did it for the first time this summer in 2024. So it was during 1 week, we had 6 different courses. These 3 were the first half of the week, and these 3 were the second half of the week. And you could only take one course because they were 15-hour courses, so 2.5 full day courses. And we had some rather prominent speakers. If you want more information, you can just Google ESPIDAM and you will see about this year's program. But it has been decided that it will also happen next year. And in fact, actually, funding is granted for 3 more years or possibly 2 more years. And next year it will take place these dates, June 23 to 27. But we will put up announcement for the new course around Christmas, but it will look fairly similar. Maybe we will add 2 courses and remove 1 course. We will see. I would also like to say, since this is an Italian community, that I will actually be visiting University of Trento in February and March 2025. So I would be happy to meet colleagues there at that time. Now let me start. So let me start with the first project. It is, or one possibility to name it is to optimizing preventive measures in time and magnitude. So you are epidemic modelers, most of you, so I think this set of differential equations should be well known to you. I hope it is, otherwise other things in this talk will not be well known, because this is the most famous epidemic model. It's the simplest deterministic model around. If you solve it, you get the final size by looking at the fraction of recovered individual for large values of t, whereas the number of it, or the fraction of infectious people looks like this. So first you have an increase, and then you have a peak, and then you have a decrease. Hopefully this is familiar to you. So what we studied is this model, but where we are able to modify the parameter beta. So we are somehow, maybe we are the king of a country, or we are God, or we are the state epidemiologist. So we can reduce the contact rate over time. So here is the new model. This is exactly the old model, except that we have an amount of prevention which varies over time. So there is no vaccine available and there is no seasonality. We take the simplest situation of all, and then we introduce a prevention strategy, P, which is a preventive strategy over time. And what does it mean? Well, it means that the contacts are reduced by a fraction P of t at time t. So the current contact rate at time t is not beta, but it's beta times 1 minus p. So 1 minus p is the remaining fraction of contacts. And then everything will depend on this preventive strategy. But if you give me a preventive strategy, I can at least numerically solve this set of differential equations. If you give me a complicated strategy, I will have to do it numerically. If you give me a very simple, let's say, constant preventive strategy, I can maybe solve it analytically. But anyway, I can compute at least numerically how many will get infected for a given prevention strategy. But there is also a cost for society to a prevention strategy. It is not uniquely defined, but we have looked at the situation where we say that the cost of the prevention strategy is linear in the amount of prevention. So this means, what does linear mean? It means that a 50% reduction for 1 month costs society equally much to have a 25% reduction for 2 months. Whether that is true or not, I have no idea about, but this is the situation we looked at. So then you have a rather natural optimization problem. Among all preventive strategies that don't exceed some fixed cost, so maybe you have 2 months full lockdown to your availability, and you could do it for 4 months, 50% lockdown, 8 months, 25% lockdown, or you get a week lockdown followed by a week free, a week lockdown. So many different preventive strategies, but you're only allowed to use preventive strategies that do not exceed some fixed value. Then the question is, which of these preventive strategy minimizes the final size? So that is the problem that we have been studying. First, let me comment on this model. Of course, this is the simplest of all models. It has many simplifications. I would say that the most crucial simplifications for our conclusions to be valid are the following 4. First of all, we assume that there is no vaccine available, nor do we expect a vaccine to arrive in the near future. If we did know that the vaccine is coming in 3 months, then of course we should have all the preventive measures before the arrival of the vaccine, for instance. Also, we are considering a fairly short time interval so that we can approximately assume that there is no immunity waning. Also, we neglect seasonality. If you have seasonality, then of course your preventive measures should be timed with the seasonal variations of the potential for disease spreading. And as I already said, we are assuming a linear cost function. So you would sum over all days and you would sum the amount of lockdown that you have that day. Another thing is that in what we studied, we said we want to minimize the total number of infected people or the total fraction of infected people. An alternative minimizing object would be to minimize the peak prevalence. And I will come back to that as well, but what we did mainly was to minimize the total number of infected people. So here is this incidence curve for the situation where there is no preventive measures. So here is how the fraction of infected people evolves over time when there is no preventive measures, and here are a few suggestions for different preventive measures. So for instance, preventive strategy 1 says have a 2-month full lockdown. Prevention strategy 4 says to have a 50% lockdown for 4 months, starting around after 2 months. Here is another preventive measures which sort of mimics the incidence curve. But please have in mind that whatever preventive measures you put in will affect this curve. So I don't have a curve, the incidence curve for each preventive measures. This is the incidence curve when there is no preventive measures. And here's one that you have a 25% lockdown for a longer period of time. So the question that we studied is which preventive strategy not exceeding some fixed cost minimizes the final epidemic size. So we solved this mathematically, so it's a mathematical proof that we spend a lot of time on. You cannot criticize the proof unless you find an error in it, of course. You could criticize these assumptions. maybe you should say, why don't you have more realism that you have seasonality and whatnot? I'm fine with that. But later I will tell what is the solution, and that's not debatable given the assumptions because it is mathematically proven. Anyway, I will not tell you what the solution is right now. So if you get bored from my other parts of the talk, you can try to think of what do you think is the optimal solution? Which preventive strategy is optimal in terms of minimizing the total number of infected? Remember that you cannot have 100% lockdown forever. Maybe say you have a 2 months full lockdown. How should you distribute that over time and in magnitude? I will come back to this problem at the end of my presentation. Now for something more applied. So this first problem that I am now leaving is in some sense a theoretical problem, but it could shed some light anyway on preventive measures. Here is a more concrete things that I looked at together with a PhD student of mine. And the question is the following. Maybe the best formulation is to say, how many lives did the vaccine save? Or an alternative, you can say, how many more deaths would we have seen if there was no COVID-19 vaccine? So that is sort of our general question. When we started to think about this, we realized that once Omicron arrived, the question was much harder because the vaccine was not as effective against it. And Omicron arrived more or less January 1st, 2022. And the vaccine arrived more or less January 1st, 2021. So in order to avoid the problem with Omicron, we said, let's consider only the first vaccine year, which is then 2021. And of course, if there was no vaccine during 2021, all countries, at least my country, where there was not that much restrictions, we would have had more restrictions if there was no vaccine. However, that's hard for us to say how much more restrictions would there have been if there was no vaccine. I wouldn't dare saying that. So a simpler and in some way more fair comparison would be to say how many more people would have died if there was no vaccine during 2021, assuming that everything else was kept fixed, meaning that we behaved exactly in the same way as we actually did in 2021, but if there was no vaccine, what would then have happened? So our approach to solve this was to first model what actually happened during 2021 with vaccination. So we call that the factual analysis of disease spreading. So we estimate the infection pressure. I will come back a little bit to this, but I won't go into detail. We estimated sort of the infection pressure and some other things over the full year, including what we knew about vaccination. And then we do the same thing, but now we simulate an epidemic over time, also during 21, with the observed infection pressure over time, but now without having vaccinations. That was our approach. I will come back a little bit to it. And we focused on Sweden since we have better control there, but you can do more or less the same thing in any country. Of course, the available data might differ. Oops. So the data that we used in our analysis was age-specific reported incidence and data on age-specific vaccination during 2021. We used several external estimates that we sort of just picked from the literature. So for instance, reported incidence does not cover all cases. There are also infected people that are not reported. So how much under-reporting there was, I'm not specialist in that, but there are some estimates available from the Swedish Public Health Agency, which varies over time that we used. Of course, these are not perfect, they're estimates, but that's what we have. Since we're interested in case fatalities, we need to know something about the infection fatality rate. This is, of course, very age specific, and we used estimates of that from the literature. Also, we took estimates of the vaccine efficacy, both with respect to the risk of getting infected, the risk of infecting others, and the risk of dying. So there are three different vaccine. For some reason, I only wrote two. There are three different vaccine efficacy estimates that we are using, and we took them from the literature. We also have some information about social contacts between age groups, and we used a social contact study. I think we used one from Sweden, or else it was from a neighboring country. I don't remember exactly. And also, we need to start on, we started on January 1st, 2021, and then we need to know how, at least in Sweden, we have had a rather bad big outbreak during 2020, or actually two waves. So there was some immunity by January 2021. I think it was of the order 15%, but anyway, we took those estimates from the Swedish Public Health Agency, and some more information about generation time distribution and reporting delays and other things. So most things here we took from other sources, but the data that we used in our analysis was reported incidence over time and age-specific vaccination. And here is how that looked. So the reported incidence over time is this red curve here. And if we, to this red curve, apply the amount of underreporting, we get estimates of the true number of infected people. And that is the blue curve. We see here that there's a bigger difference here than it is here, and the values are more or less the same. So it means that the Swedish Public Health Agency apparently estimated that the underreporting was bigger towards the end of 2020 than in the beginning of, the end of 2021 compared to the beginning of 2021. And I think that's true because here the tests were sent in. You ordered a test and then you sent it in, so it was automatically recorded. But towards the end here, we started having these home that you bought these self-tests. So then more and more of the tests were not registered. So anyway, we use this blue as our data, even of course, if it is not true data, it is somehow estimated from the amount of underreporting and the amount of the reported incidence. However, these data, vaccination data, I would consider them as very reliable. So this is what fraction or what percentage of different age groups that are vaccinated over time. So we see that it's the black curve starts increasing first, and that is of course the oldest people. So by April 1st, close to 75% of the 90 plus were vaccinated, and fairly big fraction of also the 80 to 89 were vaccinated, whereas the younger age groups were vaccinated much later. I think these curves look similar for most countries, would be my guess. So this data we also make use of. By the way, I don't see if there are any questions. I will, after I'm finished with each project, I will ask if there are any questions, but maybe Francesca can, if someone has a question in the chat or something, then please interrupt me.
Okay, yes, I'm monitoring the chat.
Yeah, very good. So this red curve is one of the data sources we are using, and these curves we are also using. By the way, this reported incident, I showed the cumulative numbers, but we have these curves for age-specific numbers, and we also have these blue curves for the age-specific numbers, and the underreporting is different in different age groups, but I didn't it would be too complicated to have 8 of these parallel curves, so I didn't show them. Okay, so that was the data, and then we had several estimates from external sources, and then we have a model. So what is a model? Well, I use U for unvaccinated and V for vaccinated. A are for age groups, and you saw the age group sizes is 12 to 15, 16 to 17. I don't know exactly why these age groups were like this, but this is how it was recorded. So I think we kept this division into age groups, but I no longer remember the exact details of that. And we have a contact matrix from social contact studies, which captures. So this is a matrix C, and the element C of A prime A, it is the average number of daily contacts that one A prime individual has with A individuals. So if you take my age category 50 to 59, and you take age category 30 to 39, so the contact between 50 to 59-year-old and 30 to 39, if that number is 2, it means that I, on average, or people like me on average, have 2 close contacts per day with people in age group 30 to 39. What is a close contact is well defined in these social contact studies. I think it is that you are within arm length distance for at least 1 minute. There is a formal definition, but of course it's not the same as you will infect when you have such a contact. You will not infect a contact which is further away, but it is, at least it's reasonable to believe that the number of people that you have infectious contact with should be proportional to that. So then there is this proportionality constant, which we call beta of t. And in many models, simple epidemic models, you keep this constant, but the whole idea here is that we want to let it vary over time, and actually our main task in this statistical analysis is to estimate it. So our model assumes that sort of the relation that you don't, if if there is preventive measures, you don't change the relation at which you meet different age groups, you just have an overall reduction. This can of course be questioned, but that is anyway what we did, and also what many other people do, I think, for simplicity. And what is our model? Well, for the unvaccinated people in age group A, the rate of infection, all infected people in age group A, they come from this, well, all of the unvaccinated infections come from here. So it's the derivative of this with a minus sign, that is the rate of infections. At time t, it is proportional to this overall population contact rate. It is proportional to the current number of susceptibles, or if you bring this over here, which might have been more pedagogic, it is the current fraction of all A individuals that are currently unvaccinated and susceptible. And this here is the infection pressure we sum over all our other age groups, and this is the infection pressure coming from individuals in age group A prime. So it is the number of the number of unvaccinated infectious people of age group A prime. And then it's a deflation because there might be some vaccinated people that are infectious, that were infected and are infectious, but their infection pressure is typically much lower. So I think we used some standard estimate, which was around 0.5. So if I think if I remember correctly, the risk of getting infected, it drops by 90%, but if you do get infected, your infectivity drops by 50% compared to unvaccinated. I think these were the numbers we used. And correspondingly, if you are a vaccinated person, you have the same vaccination pressure, but it's only the vaccinated susceptibles or uninfected that are at risk. But then you have this deflating factor, which I said was, we used, if I remember correctly, we used 90% here. So you have a much lower risk of getting infected if you are vaccinated. So I only show these two equations for, there are other terms here. You leave this state also, for instance, if you're vaccinated. So if you're vaccinated, and we take that from data, and if you're vaccinated, you go into this age group, but also you leave other states, and I don't show everything. So other things in the model would be that you have vaccination. In our model, we actually have vaccination 1 and 2 doses, and we have a latent, so we use an SEIR. So first you have a latent state followed by an infectious period. We have, and then this is the true number of infected, but then we have reporting. So not every infected person is reported, only with a certain fraction, which depends on the underreporting. And if you're reported with some random delay, which has a distribution. So there are some more complicated factors, but I think these are the two main expressions of the model, the rate at which you get affected, and perhaps the most important thing is that we let this vary with time. So with this data and with these external estimates, we perform a large numerically intensive statistical analysis. It's called a state space models because there is an underlying true, and we make random observation from this. We use MCMC using something called STAN. And at the end of the day, we get estimates of this overall contact rate as it varies during 2021. So then we get estimates of how many people get infected using the underreporting. We get estimates of this beta out of t. And if we use these two quantities, we can also infer how many people that would die not using data on case fatalities. So just using the reported cases and the amount of underreporting in the different age structures, and including in this estimate the beta t, by adding the rate, if we know the risk of dying in the different age groups, we can also get estimates of how many people we think would have died in our analysis. Then we can compare that with the reported case fatalities, and it looks like this. These are the reported cases, and this is the estimated from our factual analysis. Is this a good fit or not? That's hard for me to say anything about. I mean, it's definitely not perfect, but it's not that we report twice as much or twice as low. So I would say that maybe it's fairly good. The difference, the deviations are probably mainly due to incorrectness in the amount of believed underreporting, but it could also be, well, here I only showed the accumulated number. If you divide it into different age groups, there will be some differences indicating that the infection fatality rates in the different age groups might not be perfectly correct. Anyway, if we look at the overall number of case fatalities, our estimated model, so using our estimates, we get that approximately 5,500 should have died. And if we look at the the reported number of cases total, it is 5,400. So the total number is very well estimated, I would say. But over time, as you see, it's not at all perfect, but decent estimated, and the cumulative number seems to be okay. So that is our factual analysis, and we get this estimated estimate of the overall infection rate beta t. Now we do a counterfactual analysis. And what do we do then? Well, we use the same beta hat of t. So we assume that we behave in the same way as we estimated that we actually did during 2021. And now we simulate an epidemic forward in time. So now we don't use how many people were actually infected or how many were reported. Now we use a stochastic model to simulate, and we use the same external estimates of the infection fatality rate, the delay, blah, blah, blah. With one difference, we assume that there is no longer any vaccination in place. And what do we then get? What do we then observe? Well, on the next slide, I will show a graph, but first I will summarize what will happen. During the first half of 2021, we observe an additional 4,000 individuals that would have died. Remember that before it was in total 5,500 people that died. If there was no vaccine and we behaved exactly in the same way as we did, we estimate that in the first half year, an additional 4,000 individuals would have died. Nearly all of them would be 80 plus. So in some sense, this is a direct vaccine effect. The overall incidence does not drop very much during this first half, but we protect the ones that are vaccinated, and this were the 80 plus. However, in the second half of 21, it's a completely different story. In the second half of 21, according to our simulations, and we did, of course, not only one simulation, but multiple simulations, then 43,000 additional people died. Why? Because there is a massive wave in August and September, infecting nearly everyone in the country. And of the people dying, it's not only the 80 plus, it's mainly 60 plus, because the risk of dying is much lower for younger age groups. So here, of course, there isn't a direct effect, but the big difference is the indirect effect, in the sense that with the vaccine, we did not observe this massive wave, and it's the massive waves that infects many people and kills many people. So the vaccine effect, it is the indirect vaccine effects that prevents these 43,000. So in total, if we would have behaved in the same way during 2021 as we did, but if there was no vaccine, in Sweden, our estimate is that rather than 5,500 people dying, instead, a little over 50,000 would have died. I definitely don't rely on these numbers, these predictions. So it could very well have been 40,000 or 60,000, but the conclusion is that it's a big difference, and the main reason for this big difference is that we would have observed a massive wave during the second half of 2021. So this blue curve, you will see it on the next slide. However, the scale will be very different, because I will also show this massive wave. So this blue curve will look as it's on the bottom here. So here you see the blue curve, whereas the green curve is what would have happened if there was no vaccination and we would have behaved in the same way. Maybe I should go. Of course, I want to stress this. Of course, we would never have let this happen, so we would have put in more and more restrictions. So this is what would have happened if we did nothing additional to what we did. So we have this huge, we see that there are also in the first half, there are more case fatalities than in the factual analysis, but the big difference is here, as you see. That was the end of the second part. I think I have 10 to 15 minutes, so I do have time to talk about the third project as well. But is there a question about the second? If not, you can save them to the end. So let me go to the third problem, which is more a probabilistic and theoretical work. So it has to do with heterogeneities and how they affect disease spreading. So first, sort of some general, I like more and more these general ideas, and I'm slightly less interested in nitty-gritty details. But so whatever epidemic model you use, hope, reality, in reality, there are numerous forms of heterogeneities. Whatever you have your favorite models, I'm sure that you include some heterogeneities, but also any model is a simplification of the real world. So clearly you will also leave out other heterogeneities that you're not aware of or that you think are minor or whatnot. So the question is, what is the consequence of leaving out some of these heterogeneities? Our focus in this work was not any heterogeneity, but heterogeneities with respect to mixing. I will try to explain what I mean by this. So we are assuming that all individuals have approximately the same number of contacts, people that they contact, but if you're socially active, you meet your friends more often. That is a thing we have studied. Why? Well, other people have studied the effect of super spreaders. So people that have a huge number of contacts, you compare that to a situation when there are no super spreaders, that has been investigated more. So we instead focus on, given we don't have any super spreaders, but we might compare a situation where there are a lot of local mixing compared to a situation where mixing is more on a global scale. Those are the things we have studied here. I will be more concrete soon. And for simplicity, not we start with a situation that all individuals have same type of mixing structure. I will come back to that. So the question is, what happens with an epidemic if we make the mixing more homogeneous or more local or heterogeneous? So we have studied a specific model, but the general model that I have in mind is the following, that all individuals have the same form of local structure, and all individuals have a random number of global contacts and a random number of local contacts. And the global contacts, since we are assuming a large community, we expect that the global contacts, if you have sort of 5 global contacts, it's very unlikely that by chance you will have this contact with the same person. So these global contacts will, in a large population, be with distinct individuals, whereas the local contacts, it could very well happen that you have multiple contacts. So if we consider a household model, and let's say, if my random number of local contacts is 4, if I only spread it in my household, I have 3 household members, my wife and my 2 kids, so it would be multiple contact. Maybe I didn't see my daughter today, but I met my wife, had 2 close contact with my wife and 2 close contact with my son. So the local contact could very well be multiple, and you have to specify that in some model. So the question we're asking is, for this, and the specific example we looked at is where we consider the local structure is that we have both households and workplaces. So the local contacts are divided into household contacts and workplace contacts. And we assume that all households are of size H and workplaces are of size W. And we say maybe there is an overlap in the people that belong to your households. You might share a workplace with some of them, or if it's a school, you might share. So what happens with the epidemic if you, let's say, put more contacts here and less here. So if you make this thing bigger and this thing smaller, keeping the sum equal. Or what happens if here, if you fix these numbers, but you consider an even more local structure. So maybe this is if the households are very big, but you go to, let's say, instead assume that you have very small households. So you make the local thing even more local. What happens to the potential for an epidemic in that situation?
Tom, can I ask a question here? Sorry. So when you say keeping the number, should I think of those X like numbers per time or just numbers, absolute number?
That's a good question. Here, it is the total number of global contacts that I have and the total number of local contacts I have.
In a day, or
no, does it say somewhere? Before you recover. So
I see.
In total, before you recover, but it's a good question. So here is a more specific situation. The model we studied was you have households and you have workplaces, and they might be partly overlapping. And so here is a more specific. Suppose you have a random infectious period, then my global contacts will, if I tell you what is my infectious period, then I will have a Poisson number of global contacts. And if I tell you how long I was infectious, I will have both household contacts and workplace contacts, and the total number of such contacts will be Poisson distributed. I forgot to say what the model was. So you're infectious for a random infectious period, and during this period you infect household members uniformly each time by a rate beta H, workplace members at another rate, and community global members at the third rate. In that particular situation, I try to say how that specifies the model here. I realize that my time is running out, so I will try to move here because I want to come back to the first problem. Anyway, this model, we spent a lot of time improving things. What we proved is not all that surprising. We have you can have a minor or major outbreak, and you can compute what the probability is. Also, if you have a big outbreak, the random fraction people getting infected converges in probability to some deterministic thing. This was quite hard to prove. However, our main question was, or the thing I'm at least most interested in, this final size, the final fraction getting infected in a large population, how does this depend on the model parameters? Well, first of all, you have to think, if you change the parameters, do you make things more local or more global? Here I said PG is you fix the total number of contacts and you say pi G is the fraction of my contacts that are global. If you want to make your model more local, you should of course decrease this fraction. How about the household size? If you want to make it more local, to me it's obvious that a small household is more local than a large household. So if you want to make your model more local, you should also decrease the household size. The same with the workplace. If you make workplaces smaller, you decrease that. I will skip this. The fraction of overlap, it's a little bit more complicated and my time is running out. I will skip that as well. So how does the final size depend on these things? That is what I have spent the most time of trying to show, and I have failed to biggest extent. So our conclusion is not a theorem, but it's a conjecture so far, and that is that the final size, which depends on the overall contact rate, the fraction of the contacts that are global, the size of the household, the size of the workplace. This is not the overlap, but it is one minus the overlap. So the amount of different between workplace and households, and this is the fraction of your local contacts that are in household. The final size is increasing in all these arguments. So an epidemic model, if you consider an epidemic household model, if you look at if you increase the household size, you will get a larger epidemic outbreak. If you increase the workplace size, you will also get a larger epidemic outbreak. If you move some of your contacts from local contacts to the global contacts, you will also get a bigger outbreak. It's a conjecture. We have proven parts of this, but the most important things we have not proven. But why does this seem plausible? Well, the more local structures you add, the more you will observe multiple contacts, and in some way, multiple infectious contact with the same individual is a waste of infectious contact, so that will reduce your infections. Here is an illustration of this. This graph is considering households of size 3, and the workplace, here is D equal 1 means that workplaces are also size 3, D equals 2 means that workplaces are size 6, workplace of size 9, workplace of size 12. So we see that the larger workplace we have, the bigger outbreak you get. Here is the final size. But here is this overlap. So if there is theta equal 1 means that you don't share, you are not workmate with any of your household members. That is up here. That's when you get a bigger epidemic outbreak. And here it is, what is this? Well, I will only talk about the first curve here. So here we have households of size 5 and workplaces of size 5. And the local contacts consists of both household and workplace contacts. So the question is, if you have most of your local contacts in households or most in workplaces or 50-50 in both, then the answer is you get your biggest outbreak if you split the local contacts into equally many contacts within the household and equally many within the workplace. This is when the workplaces are the same size as the households, whereas if the workplaces are bigger, which they typically are, if you want to maximize the number of infected people, you should then put less of your local contacts into the households. So this is the fraction of your local contacts are in households. So if the workplaces are of size 6 instead, we see that we should put 40% of your local contacts into households and hence 60% into workplaces. That was this third project, and I think my time is out, but let me anyway present the solution to this first problem. So I don't know if anyone has guessed what is the solution. If we were in all in one room, I would ask you, and maybe someone would dare guessing, but now I don't think anyone will dare guessing. So I will just simply tell you what is the best preventive strategy. Assuming my assumptions is the following. So you do nothing until the epidemic reaches its peak, and then you have a massive lockdown until you run out of lockdown money. That is the best strategy. I will show one more slide, which looks like this. At the bottom, it is the preventive strategy. In the middle, it's the incidence, but I will also have, there is a top panel where you have the cumulative incidence, so the cumulative number of people getting infected. There will be a black curve. The black curve is for when there is no restriction, and the blue curve is for this strategy. And there will be a red curve for another strategy, which I will come back to. But in the next slide, we said that maybe it's not possible to have 100% lockdown. We said the biggest lockdown you can achieve is a 75% lockdown. And then the answer is that you should start slightly before the peak. Anyway, here comes the figure. So the blue lockdown is the optimal lockdown. So you said you wait more or less to the peak, and then you have the full lockdown as you can, and then you stop when you run out the lockdown money. So we see that here, before you do anything, of course, the curves look the same, but when you insert the 75% lockdown, you see a dramatic drop in incidence. Once you relax, it continues declining, but slower. The red curve is nothing we have proven, but another research group has proven. This is the optimal curve if you wanted to minimize the peak incidence. So then you don't, even if you're allowed to do a 75% lockdown, you don't use all that, and you gradually reduce the lockdown in such a way that you keep the incidence at this level. And we see that the cumulative numbers, we see that the blue curve is actually better than the red curve in the sense that fewer get infected in total, but of course the red has the advantage for the hospitals that there is no, maybe they can manage this, but they might not manage this blue situation. And now my final slide is, it would probably be hard to convince a public health official saying that do nothing for 3.5 weeks and then put in a massive lockdown. So maybe they say, no, I don't trust you, Tom. I say, I've done this computation. I trust you must trust me. No, okay, but you're a nice guy, Tom. So I give you your strategy, but I will add to your strategy. I will add an additional lockdown in the before your favorite lockdown. So on the next slide, the red, I remove this red situation. I just look at the situation where you have this lockdown that I suggested, and the red curve will be when you add a lockdown before this. So here we see, here we have added a lockdown before this. And what is the effect? Well, if you start adding this lockdown here, you see that the incidence will not have grown. And because you have 75% lockdown, it will drop. But then when you stop your lockdown, there is hardly any immunity built up in your population, so you will have a big second wave. So at the end of the day, or the end of the year, you will have more or less the same number of infected people as if you did nothing. However, of course, you will have postponed things, which is also an advantage. Now my time is definitely out, so thanks for the attention.